Well, what we're looking at is an HP1722A oscilloscope. This scope has a 275 megahertz bandwidth, meaning that from 0 to 275 megahertz you're less than or equal to 3 dB down. Um, and that's either into the 50 ohm input or the 1 megohm input. It operates vertical signals from 10 millivolts per division at the minimum up to 5 volts per division, and it does it in 9 ranges on either the A or B channels. It has a bandwidth limiter button here, so it limits the bandwidth to under 20 megahertz. There's a polarity reversal switch. We have the A, the B channel inputs. We can alternate between the two channels, or we can chop for the display. We have inputs for the trigger for A or B. There's input coupling for AC, DC, or ground, and then there's the 50 ohm input. That's on both A and B channels. There's maximum input of 250 volts, and that's a combination of the DC and AC on the high input modes, and on the 50 ohm input it'll handle 5 volts RMS. You don't see that 50 ohm input on any, well, I'm not going to say any, but on many of the modern scopes, and I'm not quite sure why, but 50 ohms is a relatively common load and input, and I would think that maybe with the ham radio operators and things like that, it might have been more popular at one time. Channel A and B can be made additive or subtractive. We can. There are 7 horizontal modes utilizing these switches. We got the main mode where either A or B channel is represented on the screen. We got a delayed mode, second switch down, where only the delayed magnified portion of the signal is displayed. We've got main intensified, where you're looking at the main signal. Let's see if we can show you here. Here's the delayed. This is called mixed. We'll get to that in a minute. Here's main intensified. This is the regular signal that's in the duller light mode. And then in between, that's the part of the signal that we want to magnify and zoom in on using the delayed portion. If we were to look at only that delayed portion, we hit delayed, and there's the magnified portion of that waveform. In mixed mode, we can see both. We see the beginning of the trace where we're in the main normal horizontal sweep mode, and then suddenly it starts at the delayed, and you see the expanded delayed sweep for the rest of the trace. Back to main. And then we have an XY mode, and if I disconnect the Y, you can see the X there. That's the input A, and then here we have input A against input B, and we're using the same signal, so it's showing me a 45-degree angle. And if there was a phase shifting between the two, and there's a slight shift in there, probably because of the cable, but you would see it hoop out into possibly a circle. It's a Lissajous pattern. Lissajous patterns used to be common for trying to not only sync signals, but to determine what frequency was present by beating one signal against another. The trigger source can be channel A, channel B, or it can be a combination of both. The horizontal sweep, the larger of the controls over here, there's actually two time bases. You have the center control, which is the main time base. Let's get into the main signal. And we change our sweep rate with that. Or we have the rear delayed time base, which we'd have to put on at least mix to show you that we can change the frequency on that as well. Okay. Oh, let's see, there's 24 ranges on the horizontal sweep on the main. And that covers from 0.5 seconds per division to 10 nanoseconds per division. The delayed sweep, the rear control here, has 20 ranges, has 4 fewer ranges, but it covers from 20 milliseconds per division to 10 nanoseconds per division. And it's there just to give you an expanded view of the normal range, or the normal trace. In addition, we've got a beam finder button. No matter where you're at, trace-wise, the screen will collapse and it'll show you that you have a beam. We have an intensity control. Plenty of intensity there. We've got a focus control. We've got the scale illumination control here. What this does is there's a flood trace, that's what it is, that floods the screen, lightens up the phosphor, and allows you to see the dark radical lines more readily. Most of the time I have it off because I can see the gradical just fine without it, but it can be done. We've got an astigmatism adjustment in the back. It's through a hole, and what that does is, let's go ahead and put these things down. Now there's a dot on the screen. If that dot was flattened one way or the other along some axis, you'd use the astigmatism control to round it out, turn it into a dot. Just helps for the focus and visibility of the trace. There's also a trace alignment, and trace alignment allows the right now we've got a flat line that goes across the screen and it's right on the center gradical mark. It's perfect. The reason it's perfect is because the trace alignment has taken any misalignment in horizontal and allowed you to balance it out and make it perfectly straight and match the gradical. And then there's a ton of other features. There's a ton of buttons on here. I mean, there's things relating to bandwidth and inputs and the type of input, type of coupling, internal, external. We've got a lot of external capability, external triggers, front and rear. We've got modulation on the input on the back where you can actually modulate the beam as it traces. I've actually seen people show black and white TV kind of pictures on the screen using modulation. A lot of capability here. But one bad thing about the oscilloscope is that the original scope had a working digital multimeter in it that allowed you to read the input voltage and give you some information about the frequency. And although occasionally the thing will just pop on all by itself, it also is more likely to be off. So there's an intermittent in that circuit someplace, and I have not found it. I don't intend to find it. It's just too much work for me, and I don't have the time. But it doesn't really much matter to me. The scope is still a beautiful scope that matches the characteristics of the majority of scopes out there that did not have the digital multimeter. Would be a nice feature to have. Perhaps whoever gets it takes the time and can find what's causing the intermittent condition. I was here just yesterday, in fact, and pretty much the situation we're in here, and suddenly the display just came on all by itself. But the moment I went and tapped one of the buttons, it popped away, and no matter what I do with any of the buttons now, it hasn't come back. So, that's the only negative. As far as the rest of the scope goes, it's in excellent working condition. We'll demonstrate a little of that, and it's in good physical condition. Comes with the accessory pouch. It's mounted to the case. Has a nice handle. Case is in good shape. The front panel is in good shape. A little bit of paint rubbed off over here on the left, but it's not bad. And let's go ahead and turn ourselves back on here. Make it just a little easier for us to see the trace. Now that looks like a nice trace. Nice, clean. I can dim it, I can brighten it. I'm not quite sure how it's going to look on the video, but very nice, clean trace. But actually that's two traces. And if I go ahead and let's take this down a step, you'll notice that one of the traces now has extended to beyond the screen. It's because I went down another step and I'm in 0.05 volts per division where I had been in 0.1. And the other channel B is still in 0.1. But if I go back and match it, they overlap each other beautifully. If I take channel A to 0.2, then a display is half of the other. I can match it again by just switching channel B to 0.2. If I go to 0.5, channel B to 0.5, once again they're overlaid. It's because the unit has been calibrated and it's in pretty good shape. I will take it to 5 volts per division, and we will step up the input so we can see that. Right now that's 10 volts peak to peak on 5 volts per division. That's 2 divisions. And that would be 20 volts. So we've covered 4 divisions. And if I kill, well, since A is the trigger, if I kill A, we still see B in the background, but it's fuzzy now because I haven't got the trigger on. We can switch to B trigger, we got it. If I take the B channel out, you can see A is still holding. Or we superimpose one another and we got a nice trace. Frequency-wise, we've tested this thing up to 275 plus megahertz. Maybe we'll do that again. Okay, we've got the unit set up so that we are feeding into it, and we have in tandem with it a 50 ohm load. We're on the high impedance input, and we're outputting from a 50 ohm output that's calibrated from this PTS 500. We're at 1 megahertz right now. So we're looking at a 1 megahertz signal, and we see that we're calibrated to go up 3 and down 3. Okay. So now, if I turn my frequency to 275, and what I see is I have a line defined across the top and bottom at about 2.4 centimeters. divisions, I should say. And you know, it is a signal, 275 megahertz signal. And let's see, there's magnified by 10. And let's take a look at a little math over here. If I have 3 divisions, up and down, and then in order to have a 3 dB loss, I should drop to 2.12 divisions. And we are at 2.4 divisions, so we're better than 3 dB at 275. In fact, what if I was to go to 300? All right. At 300, we are at 2.2 divisions up and down. So it looks to me like we made our bandwidth in the high impedance selection. We're going to go directly into the unit, and we're going to put ourselves in 50 ohms mode on the unit input, and we see once again we are at 2.4 up and down. So that's exactly the same thing we had on the high impedance input. We're getting it on the 50 ohm input. And so that would mean we're exceeding the 275. Worth knowing. All right, we're in the XY mode right now, and I'm feeding in a 1 megahertz signal from the PTS500 on the x-axis, and I'm feeding in a 1 megahertz signal from this DDS generator. And PTS500 is connected to my master oscillator on the bench, heavily calibrated. This little K-Moon unit probably uses a little crystal, but I'm sure it's got nowhere near the same accuracy, so we got a little bit of deviation there, and we see that as the oval, you know, expanding and collapsing rather quickly. So what I'm going to do is I'm going to dial in. There's 1 hertz. Go 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz. 6 hertz, it starts picking up speed again. So we're a little over 5 hertz difference between the K-Moon and my bench oscillator. And that's why we see the Lissajous pattern slowly revolving, because of the little bit of difference there. But the XY circuit's working. And in order to display that, I remove the A input. I've got no input selected. If I selected the A, it kind of impedes it. So we've got that going. So here we go. We've got it's a good oscilloscope. Does not have the digital multimeter. Again, that's too bad. But there's nothing wrong with the scope. It's a 275 megahertz scope. Has some beautiful functions on it. It'll make somebody a nice bench partner. So happy bidding. Oh, yes, I will be providing a manual, a user and a service manual will be coming with this on a CD. So won't be in the lurch. And if you want to work on that DMM and maybe figure out what's going on, keep me apprised. Let me know what you find. I'd be curious myself. Thank you for listening, and see you again.